let's evaluate this integral. And before we do this, I want to test your knowledge a little bit. What is the solid of integration here? How would we find it? Well, let's look at the limits of integration. So let's talk about how we would find the solid that we're integrating over. What does z lie between according to the limits of integration? What's the bottom limit on z? X squared plus y squared. So what is that? What is z equals x squared plus y squared? Yeah, it's no. So hold on, we'll think about it. What's the upper bound on z? 2 minus x squared. And that really should, let me see here if I copied that right. Yeah, that really should be a minus right there. Sorry about that. Minus y squared. Otherwise, I'm not sure what that would look like. There. Okay. So, so that's the upper bound on the z. So, okay, so what are these two objects? What are the equalities? Well, this is something you guys, if you don't get this down pat, you're going to have a really tough time with not only the homework but the next test, okay? And this is chapter 12 stuff. Z equals x squared plus y squared. Carl, are you signaling for a touchdown? Yeah. No, you're signaling, this is what Carl's doing. He's going like this. He's making a bowl shape with his hands, and that's exactly right. This is a paraboloid, right? In fact, it's a circular, it's not only an elliptical paraboloid, it's a circular paraboloid. So it opens up, the vertex is at the origin. This guy, if you think about it, at the equality, you have z is equal to 2. If I factor out the negative, it's 2 minus the paraboloid, right? 2 minus x squared plus y squared in parentheses, like that. And so that's actually an upside down paraboloid, and the vertex is at a height of 2, right? And x and y are both at 0. So that's telling me right now then that the region of integration is going to involve those two paraboloids. One of them is opening up, right? And one of them opens down. This one is the one that opens down. So this vertex would be at a height of 0, 0, 2. Whoops, 0, 0, 2. And it would open down. If I erase the extra stuff, you get kind of it almost looks like an ellipsoid, but it can't be because it's going to be a bit of a sharp edge right here. But it does kind of look a little bit egg-shaped. Now, are we integrating over the whole region? I don't know. That's what the other limits of integration tell us. Well, we know y lies between what? Y, okay, middle limit, right? Oh, y is going to be between the negative square root of 1 minus x squared and the positive square root of 1 minus x squared. And what does x lie between? X lies between negative 1 and 1. Okay, so x lies between negative 1 and 1. Oh, so together, what do these describe? So imagine projecting, looking straight down on this kind of egg-shaped solid. Then what's going to get projected down is the disk, and the outer part of the disk will be this curve of intersection. And actually that curve is going to turn out to be the circle of radius 1. You can tell from these equations. And the fact that y goes y goes from the left-hand side of the circle, or no, I'm sorry, the lower part of the circle to the upper part of the circle, and x goes from negative 1 to 1. This describes the entire circle then. I know these two inequalities describe the entire circle of radius 1. In standard form, it would be x squared plus y squared equals 1. Okay? So how do I know that? Well, think about it. If you have a dy dx order, that corresponds to the usual in the xy plane That corresponds to the usual vertical rectangle setup. The bottom of the rectangle is given by this guy. Top of the rectangle by this guy. X runs from -1 to 1. So that's the entire circle, or the interior of the entire circle, the entire disk, we could say. Okay? So make sure you can identify the object based on the limits of integration, based on those values that you're given if the integral is already set up for you. Let me ask you this. Which of the two systems, spherical or cylindrical, makes sense to convert to here? Okay, let me introduce a term to you. In space, if a solid were radially simple, what do you think I would mean by that? So if in space a solid were radially simple, what kind of object might that be? Yeah, a sphere. A sphere is radially simple, isn't it? Let me see if I can draw a picture for you. I really want you guys to understand this conceptually. That's why I'm belaboring this. So a sphere, if you think of this as your happy little sphere, a radius of the sphere might come out like so, right? Hit the edge here. Now, no matter what kind of radius I draw, I would hit the same surface, the sphere, right? So and if, that's what I mean by radially simple. This object here, this egg-shaped object, is not radially simple. Because, okay, yeah, if I just went up top, then yeah, I'd hit the same surface every time, wouldn't I? If I went from the origin to the surface and drew a radius, I get, well, it's not really a radius, it's a, I don't know, it's a line segment starting at the origin. If I just stuck with the upper part of this thing, I'd hit the same surface, right? But no, it's got to be the same throughout. So if I started there and went down there, that's different, right? That's the paraboloid that opens up on the bottom. That's the paraboloid that opens down on top. It's not radially simple. So if something's not radially simple, you want to think twice about using spherical coordinates. Okay? All right. So, I mean, it's not that you wouldn't use it, but there is a better way, and it is going to be cylindrical coordinates. Why? Well, the first thing I see is a bunch of x squareds plus y squareds. And what is x squared plus y squared? R squared. Big hint right there. Okay. When you project this solid down into the xy plane to get the limits of integration for the outer two integrals, you see this sort of, so you see this circle being projected down, right? Because that's the origin right there. And of course, so you smash that down. It's actually, the circle's the boundary, and it's actually that disk, right? And that's exactly what I drew right here. The disk x squared plus y squared equals 1. So again, I see x squared plus y squared equals 1. I'm thinking r squared. Okay? Is this discussion helping to clarify a little bit, hopefully? Okay. Good. Then it's worth belaboring it. Okay. I used to just go right to it. All right. So now let's take another look at this thing. And then if we decide on, so we're going to decide on using cylindrical coordinates. What do the inner limits become if we use cylindrical coordinates? Let's start with the, you can start either with the integrand or the inner limits of integration. That's where I would start. So we'll set up our three integral symbols. What would the integrand become? R squared to the 3f's. It wouldn't be a bad idea then to put in your volume element right away so you don't forget. Because there's a piece that's easy to forget. What's the volume element? Think polar coordinates, except you need a dz in there because it's a triple integral. So it's got to have an extra factor of r, and then dz, and then what were the area? What was the area element from polar? dr d theta. So make that connection with what you've learned with polar, and there's just an extra factor dz in there because it's a triple integral. So that'll help, help things mesh in your mind to remember this stuff. Now, okay, so how would you write the lower limit in essentially polar coordinates, right? Cylindrical coordinates, I guess. Because it is z equals something to z equals something, right? Z equals what? What is x squared plus y squared? So r squared would be the lower. And you could think of this as the upper limit as 2 minus r squared. Good. Does that make sense? And by the way, you've essentially set up these integrals before. It's just we didn't know about cylindrical coordinates in 15.6, so you switched to polar after you did the inner integral, right? If you've done 15.6 at all. Okay, so this is how you would do it all at once in cylindrical coordinates. Now, we know what the region looks like when you project it down onto the xy plane. We know it's a circle, radius 1. We could create a spoke or a representative sector. I like the spoke idea to see what r runs from. What does r run from? Yeah, it's a radius 1 here, so 0 to 1. And then to go over the entire disk, r is the entire disk. So what does theta have to run from? Think angularly, 0 all the way around to 2 pi. Well, gosh, look at this. I haven't even cleaned up the integrand yet, but look at this compared to the original. Isn't it a lot easier? Yeah, it looks a lot better too. All right, so cleaning it up, we get the integral from 0 to 2 pi, integral from 0 to 1, integral from r squared to 2 minus r squared, and then what does this become in here? What's r squared to the 3 halves? 3 r to the third times another r to the fourth, and then dz dr d theta. And it becomes just a reasonably easy integral to evaluate. We can't break it up quite yet, so let's just evaluate the inner integral here. Try to make a little bit of room. So careful here. What do we integrate? Let me focus on the inner integral. So focus on this guy. What are we integrating with respect to? Z. So you could actually pull the r to the fourth outside of that, couldn't you? If you want to. So when I rewrite it, then I could think of it like this. The integral from 0 to 2 pi, integral from 0 to 1. I could put the r to the fourth on the outside, and then if I integrate with respect to z, I just get z then evaluated from what? R squared to 2 minus r squared. So it could look like that. There's no reason to include r to the fourth inside those brackets, in other words. Okay, so let's do that. So we get the integral from 0 to 2 pi, integral 0 to 1, r to the fourth. What do we get inside the brackets? The evaluation brackets, I like to call them. So we're going to have, what, 2 minus r squared, and then minus just r squared. Okay, yeah, so 2 minus 2r squared, and then dr d theta. So this becomes 2 minus 2r squared. Whoops. Does everybody agree with that? Now, the remaining double integral has constant limits of integration and is just a function of r. So can we split it up into a product of integrals? Yes, we can. And it just cleans it up. You don't have to do it this way. It just makes it look better. So you just get in terms of theta, what integral with respect to theta do you get? 0 to 2 pi. Why is there an extra d in here? I don't know. I don't know. Sometimes there's a slip of the pen. Okay. And then just d theta. 1 d theta, or just integral 0 to pi d theta, right? So that's just going to be 2 pi. And then what does this guy become in here when you distribute? So think of distributing the r to the fourth to that guy. What do you get? 2r to the fourth minus r to the sixth. Okay. dr. Okay, so I just like doing it that way because it really cleans it up. There's less to think about. So this is just 2 pi. Why not write it down right now. And then when you integrate this, what do we get? Let's see, maybe 2 over 5 r to the 5th minus what? 2 over 7 r to the 7th, evaluated from just 0 to 1. And so that becomes 2 pi times what? Just 2/5 minus 2/7? What is that? I don't know. Now this is the hardest part, arithmetic, right? So multiply by 7 over 7. What do we get? 14 over 35? Minus multiply by 5 over 5. What do we get? 10 over... wait a minute. The common denominator 35, so multiply by 5 over 5. So wouldn't that be 10 over 35? Oh, you're giving me the final answer. Okay, I understand. You were too fast for me. So 2 pi times 4 over 35, or 8 pi over 35. Find the volume of the solid inside x squared plus y squared plus z squared equals 16, and outside z equals the square root of x squared plus y squared. So you've got to know what these equations represent. So what is x squared plus y squared plus z squared? What is this guy? It's a sphere, right? Radius 4, and centered at the origin. Well, what is this guy? Z equals the square root of x squared plus y squared. What is it? Cone. It's the top half of a cone, right? Be the top half of a cone. If you squared both sides, you'd get the full equation. Z squared equals x squared plus y squared. And that would be both the top and bottom half of the cone. But since it's the positive square root, it's the top half of the cone. So you just need to draw a passable picture of this thing, okay? So let's see if we can do that. Let's draw the sphere first. So, okay, here's my, let's see. Here's my sphere. Let me draw a circle and then an equator, and that's your sphere. Okay, doesn't have to be perfect. And then the cone, the top half of the cone, the vertex is at the origin, right? So the vertex of the cone, the top half of the cone would be here, and then it goes up, and at some point, you know, it keeps going up. It's gonna go through the sphere at some point, and I don't like that one. It'll go through, but there will be a curve of intersection, right? And the curve of intersection might look something like that. So this curve of intersection right here is on both the sphere and the cone. Okay? Now, anytime you have spheres and cones, it's a good hint to use what kind of coordinates do you think? Spherical coordinates. And look at what we want to do. We essentially want to find the volume of the solid. It's got to be inside the sphere, but outside the cone. So can you imagine what that would look like? It would be the volume, the space inside the sphere surrounding the cone. Okay, so if you think about the setup, and if you think about spherical coordinates, the setup would look something like this. Okay, we're going to have 3 integrals. The integrand is 1 when you're finding volume, except you need the volume element, which is rho squared sine phi. And then usually we go with d rho, d theta d phi, or d rho, d phi, d theta. So set up, that's kind of like a template, just so you don't forget anything. Set that up right away. And now, to get your limits of integration, you have to think, what does rho run between? Okay, so rho, if you're looking at the volume inside the sphere surrounding the cone, Is it radially simple? Will I hit the same surface every time if I draw a radius in space? Will I hit the sphere? I will. And what is the radius of that sphere? 4. So rho runs from 0 to 4. Does that make sense to you? Now the others, don't think the limits will always be constant. In this case, I think they will. But we do have some difficulty here. Phi. What does phi run from? Remember, the origin is here, and the z-axis is coming through like this, right? So we need phi. What is phi going to run from? Well, we don't want to include this angle, do we? We want to exclude that, because if phi runs from 0 to whatever this the angular slant of this cone is, then those are points that are inside the cone. We don't want that. We're excluding those values. So we actually want to start phi here. You could call that phi value phi 1, right? Which would be this. We want to start at phi 1 and go all the way down, carve out all the way down. Here's the negative z-axis. We want to carve out all the way down to this position. That's as far as we're allowed to take phi. So we want to take phi from, let me do it in blue. We want to take phi from here and carve it all the way down to here. I know what the bottom angle would be. It would be pi. So, well, the bottom, when I say bottom angle, that would actually be the upper limit of integration. But to get the lower limit of integration, I have to get whatever this starting value for phi 1 is. So how do I get it? Well, I need to figure out where this point is. And this point is on the intersection of the cone, the intersection curve of the cone and the sphere. So I think I can get it. Okay. On the intersection curve, we can say that the z values are equal. So I could plug this into here. And if I do that, I'll get x squared plus y squared plus z squared. Well, that would get rid of this this square root right here, wouldn't it? That exponent would get rid of that square root, and I'd have another x squared plus y squared. And that would give me 2x squared plus 2y squared equals 16. So on this intersection curve right there, I get 2x squared plus 2y squared is equal to 16, or x squared plus y squared is equal to 8. So that would be the curve without the height value, whatever the height is, we're not sure about yet. But that would be the curve, this circle of intersection, this curve of intersection. Okay? So then how does that help me find out what phi is? Well, take a look at a particular triangle then. Take a look at this triangle here. And there, by the way, there are other ways to do this, but I'm trying to show you some tips and tricks here. If you take a look at this triangle here, then you know a little something about this triangle. This triangle, this side of the triangle would be the radius of this circle. So if you took a look at that radius, what's the radius of this circle? Isn't it the square root of 8? Would you buy that? And I know that this hypotenuse here is the length, well, this radius here, rather, is the length of this hypotenuse here. And this is a right triangle. And so that radius is what, 4? Well, a quick use of the Pythagorean theorem will show you that this has to be root 8. Doesn't it? Because root 8 squared plus root 8 squared is 16, right? oh, that would be the square of the hypotenuse. The square root of 16 is 4. Okay, so how does that help me? Well, if I know that the rise is the same as the run, I know that this angle is pi fourths. But let's say you didn't know that. Couldn't you use right triangle trig to get that? Let's say you didn't know that that angle, that these sides were exactly the same length. Let's say for some reason you didn't know what this was. Then to get what I called phi1 then, which would be this angle here, you could just take, okay, this would be, I suppose, the adjacent side, wouldn't it? And the hypotenuse. So what trig function relates those? Cosine. So cosine of phi1 would be what? Square root of 8 over 4, which is 2 radical 2 over 4, which is just radical 2 over 2. And then it becomes obvious, oh, phi1 is pi fourths that way. So however you get it, I mean, that was kind of the long way to do it, but I wanted to illustrate the tips and some tips and tricks you can use. However you get it, it looks like this starting angle here has got to be pi fourths. Okay? So it's going to go phi, long story short, phi will go from pi fourths to pi. And then what's theta going to run from? Is it obvious? It's the entire region or volume surrounding the cone and inside the sphere that we're looking for. So isn't theta going to go all the way around? I don't even think I need to project it down to figure that out. 0 to 2 pi. Okay? That's not such a hard integral to evaluate, so I'm going to just give it to you. Turns out that, and you could evaluate this for extra practice. So this is your setup. And you could split this up into separate integrals. And if you evaluate it, you should get 64 pi on the outside times 2 plus radical 2 over 3. So if you need extra practice, try evaluating that integral.